Hello everyone. So we are discussing about Hello everyone. We are discussing about the optical sources. In this video, we will cover the basics of semiconductor physics and then we proceed to LED. So in LED, we will discuss a structure, its efficiency, modulation, and its power calculation. And we have already discussed about the consideration or points that is to be kept in mind before selecting the optical source for the optical communication system. So you already know LED is basically a PN junction diode in which after the recombination of holes and electrons, energy is emitted in the form of light. So basically, we are considering the direct band gap semiconductor material, and in the recombination region, when the hole and electron recombine, the energy is radiated. When the energy is radiated in the form of photons, then it is radiatively power. So when LED, there are two types of power is generated, one either by heat or either by photon. And in the laser is also one of the optical source, but it is coherent and highly directional as compared to LED. And LED and laser both are used as an optical source as per the applications. In this slide, we will discuss little about the spectral bandwidth. So here you can see this red graph. This is the spectral width of this is the spectral width of this single frequency laser laser and this broad range 30 to 50 nanometer wide. This is showing the spectral width of LED, and this is the spectral width of laser. So here you can see the laser output is the laser spectral width is less as compared to LED, and we will get output laser output is high laser output as compared to LED output because of variation in this laser spectral bandwidth. So now we go through the quick review of semiconductor physics. So as you already know, PN junction diode is formed when we join P-type semiconductor and N-type semiconductor material. And here you see this is the energy band diagram of any PN junction device. So this is the valence band and this is the conduction band, and the space between conduction band and valence band known as a forbidden energy gap. And here electron uh, or holes, as it depends on the type of material, will move from valence band to conduction band. So there is a transition of electron from this valence band to conduction band. So here we will discuss three types of cases. In first case, the hole concentration and electron concentration distribution is same. So this is the energy level diagram in which electron is there is a transition of electron from valence band to conduction band, and there is a equal electron and hole concentration. Here you can see in this graph B, This graph is showing this 2 kBt. This is showing the whole concentration distribution, and this is the electron concentration distribution. And EC minus EV is equal to EG, forbidden energy gap. Now, this is the intrinsic semiconductor material. All these conditions which are discussed till now are about the intrinsic semiconductor device material. But if there is an n-type semiconductor material, so what will happen? There will be one donor energy level nearby the conduction level. Here the number of electrons are greater as compared to number of holes. So the electron concentration distribution, here you can see in this graph B, the electron concentration distribution is higher as compared to hole concentration distribution. And there will be one donor energy level below the conduction band. So the ionization of donor impurity create this increased electron concentration distribution. Now, if the material is of p type, then what will happen? There will be high hole concentration distribution and acceptor energy level above the valence band. And this is because of increased hole concentration. So here till now we have seen this is intrinsic semiconductor, this is n-type semiconductor material energy band diagram, this is p-type semiconductor material energy band diagram. So here you can see few formulas. Here n is equal to p, this n is equal to p. These are denoting the number of electrons and number of holes for the intrinsic semiconductor. So this is given by exponential minus Eg 2 kBt. Eg is the energy by forbidden energy gap, and T is the temperature and Kb is the constant. And for extrinsic semiconductor material, Ni square is equal to Pn. Ni is the intrinsic concentration and Pn are the hole and electron concentration. So this is the basic PN junction. This is N-type material. This is P-type material. When these two materials join, depletion region will be formed, and when we measure the potential across this depletion region, we will get some potential, and that potential is known as the barrier potential. When we draw, when we analyze the electric field across this PN junction diode, then we will see that the strength of electric field is maximum at the center of this depletion layer. This is the width of depletion layer, and at the center of this depletion layer the electric field is maximum, and as we move towards these terminal the field is reduced or become zero. So this is the unbiased PN junction. When we bias this PN junction diode, biasing means we are connecting the battery, external battery to this PN junction. So if this is connected in reverse bias, what will happen? The width of depletion layer will be increased. And as the width increased, the barrier potential is also increased, and it is not possible for minority carrier to move from one side to another side, from P side to N side. So there is no current. So in case of reverse bias PN junction, the current will be zero or very less in magnitude, almost zero. What happened in forward bias? The width in this N side is connected with the N negative terminal of battery, P side is connected to positive terminal of battery. And as we connect this external battery in the forward bias mode, the width of depletion layer decreased. As a result, the barrier potential is also decreased. When the barrier potential is decreased, then electrons can easily cross this depletion layer. And when electron move from one side to another side, then will be flow of the current. So this is all about the basics of semiconductor physics. Now, at the end, what we have to discuss, there are two types of semiconductor: direct band gap semiconductor and indirect band gap semiconductor. So here you can see the maximum of valence band and the minimum of conduction band coincide in case of direct band gap semiconductor. Whereas in case of indirect band gap semiconductor, the maximum of valence band is not coincide with the minimum of this conduction band. Conduction band is shown by this blue color line and valence band graph is shown by this red color line. Here you can see this is the graph, this point is the maximum of valence band and this point is the minimum of the valence band, and both are not coincide in case of indirect band gap semiconductor device, where in this you can see these two are coincide. So this is for this graph is for direct band gap and this graph is for the indirect band gap semiconductor. Now in next class we will discuss about the LED structure that is used for the optical source.